So, a very good afternoon to you all. Control of voltage using transformer was a subject we initiated in the last class, in line with which we just discussed how that tap changer facility makes the transformer so important in power system application, and in which the transformer tap changer is usually installed at the high voltage side, having noticed the advantage of low current during the switch of that operation. That is the reason it is put in high voltage side. And we just initiated this, how exactly in the system tap changer functions, that is the OLTC, on-load tap changer. During the live service, how the taps are being altered to the next and other, depending upon the requirement of supplement of voltage or decrease of voltage by tap changing like that. So that mechanism is shown symbolically in the right hand side bottom figure. You can see HV winding and LV winding. You have the HV winding second terminal, the terminal number 2. You can see terminal number 1, and another terminal is taken at the bottom, which is a neutral. So which is having some special fittings here. This you have to concentrate. How exactly taps are changed? This is a logical switching. A selector switch like symbol in the switch, and it will show you the connected point of the winding, portion of the winding for your operation. But how in real time you will find it? In real time, the winding is having a tapping, and tappings are like point number, you can say S2 dash and S1, maybe point number 1, and point number 2, point number 3, point number 4, like that. Several contacts were established with the winding, so that certain length of winding or turns of winding will be in action whenever that contact is engaged with the service. So for that, let us see that the HV side, one lead which is shown as a neutral, the line and a neutral, it is through a reactor, switch reactor. You can see this is the continuous length of winding, just imagine, and winding is taken via, you can just see here, selector switches, S2, 1 or S2 dash, S1, like that. Two selector switches operate, connect, disconnect, like that. Select, deselect, like that. Two switches are there. At the end of these two switches, I have a R, which is called center tapped reactor. It's an inductor, continuous length of inductor. Centrally, it is having a tapping. That tapping is having a vacuum switch. This switch is just going to connect, disconnect this entire HV winding with the power input. So VS, this is called vacuum switch. A contact established in a vacuum as a media, vacuum switch. Reactor is having a center tapping, tapped center via vacuum switch. It is able to connect external power inputs. Then this reactor ends half of the first and remaining half via a selector switch, S1 and S2 dash, getting connected to windings of the HV winding where tap changing contacts are there. This is one part of the requirement. The input terminal via a vacuum switch having a continuous reactor, inductor tapped centrally, one lead at the left, one lead at the right position, and each leads are having a selector switch, S1, S2, like that, and that switch is having a tapping point number 1. This is a horizontal bar, we can say. This horizontal bar is tap number 1. Horizontal bar is tap number 2, tap number 3, tap number 4, like that. It means each contact, let us say 4th. 4 is nothing but it is a contact of the winding taken, one contact at the left side, one contact at the right side. It means to say these two switches, S1, S2, which I am speaking about, S1, S2 are getting engaged to, suppose if I want to select the tap number 2 during its normal operation. So how do I do? These two switches are not operated simultaneously. So one of the switch is selected to point number 2 at the right side. Later 2 is shipped to point number 2. Suppose you want to shift the winding to 3. Then S1 is from the 2 shifted to 3, and later S2 is switched to 3. Like that, the contact of the particular winding point, suppose the point winding contact tap number 2, you are getting connected from the winding tap point number 1. Here what we'll do, rotary like switch is shown. Just select the point number 2. There is a disconnection and connection of the contact is noticed mechanically in this representation at the left. But here, that kind of discontinuity is not felt. How that is arranged? The winding leads, winding contacts points are extended left and right. Like a point number 4 is having left contact, right contact. 3 is having left, right, like that. All the time during its normal operation, one of the tap contact is established with switch S1, switch S2. Suppose say imagine point number 1 switch is engaged in the service. So left contact and right contact are engaged respectively S2 and S1. S2, S1 via the select switch, I mean you can say center tapped reactor, it is getting connected to neutral. It means the inductor is inserted in the path to ensure current is continuous, because current through inductor cannot change abruptly. We are very well known to that. In that perspective, this reactor is centrally connected to the out point, neutral point via the vacuum switch. This reactor will be having one half of that connected to left contact of the selector point and the right contact of the next tap point, like that. So this ensures continuity of flow of current to the input or wherever it is. So suppose this tap number 1 you are supposed reducing. Hope say when the tap number 1 is having a certain V1 voltage, V1 you want to reduce, then you will go for inner tapping, like that. I am going reduction. Higher point and I am trying to get lesser voltage is my requirement. Then tap need to be shifted downward, or length of the winding inward I need to reduce. So turns I have to reduce. Then it has become necessary for me to say tap number 1 I should go to tap number 2. How the operation works here? This selector switch S1, S2 I have, which have established the contact with tap number 1 at the right and at the left via the reactor is connected to the main circuit. Now for me to change the tap number 1 down to tap number 2, it is my requirement. How I will do? I will make switch S2. Look at my mouse cursor here. Switch S2 will first open. Then switch S2 is still in contact. You can see here, still S2 is in contact via this reactor. Yes or no? Only this is opened. When I open this I will choose to point number 2. You can just see here, 2 is switched to point number 2 and S2 is opened. Now what I have done now, which both S1, S2 were established their contact with the tap number 1. My choice is to go to tap number 2. S1 I will open. Still S2 is keeping contact with the point number 1 tap. Then switch 1 I will engage with the tap number 2's right side contact. So S2 is still in the point 1, S1 is at a point number 2. Then I will make a path, current delivery via this and this via momentary position. Once the contact is established with the tap number 2 via the one of the switch, I am speaking one because S1 be my priority. S1 I switch here, then remove the S2. By the time tap number 2 got connected to the load or a service via the second part of the reactor. So I got connected during the load, you can see live, it is a live switching. So it was in point number 1 and I broke this contact and established the contact with the tap number 2, still circuit is live. Then I will break S2 contact from the S1, point number 1 tap, I will break it. Still continuity of service is there because S1 got already connected to point number tap 2, then shift this S2 comfortably hooked to 2. Then by this way, what I did, tap 1 to tap 2 I have moved without disrupting the service. Suppose I am trying to go to tap number 3. What I will do? Again I will repeat the operation. S1 which is already connected to tap number 2, I unplug it, remove this, connect it to tap number 3 position. Still contact was there with the 2, with the S2. S2 I remove. By the time the switch S1 is already engaged with the tap number 3. There is a service delivery to the inputs here. Then point 2 which was having a S2 contact, we have removed it, touch it to the point number 3. This way, sequentially crawling, one side you contact, other you open, other you connect, establish the contact. Then remove the one contact, establish the next one. Like that, you can down from the required voltage, you can step in slowly to get to reduced voltage, or from the inner point, point number 4, towards the 3, towards the 1, towards the higher, I can shift in left, right mechanism of selecting the contact via the selector switch 1, selector switch 2, respectively, keeping the continuity of flow of current via the center tapped reactor using vacuum switch. So this is the provision made at the tap changer of a transformer. This is the logical way of switching. So if I would have used this mechanical kind of switching, you are very sure that I have only one contact getting engaged with the either of the point, either to the point 4 or 3 or 2. I have been engaged here with only one point. Therefore, that we have to take care. There is discontinuity. When I move the contact to the next one, there is a momentary break in the service. It is called, not called as a online. So that is a tap changer with the offline. So momentary there will be disconnection and connection like that. But that is taken as an advantage. Then reactor which is center tapped and taps were such a way arranged, sequential movement of contacts of the selector switches like S1, S2 in this diagram, getting contact with the upcoming tap number or going other tap number is made as a provision. This way, on-load tap changing facility is engaged in this logic. This is a wonderful utility. It can be mechanized in a proper way. It may be manual or it can be mechanized. So normally it is a mechanized where depending upon your required terminal voltage or a voltage which you are supposed to alter the tap position, a microcontroller or a computer based system, if we incorporate, automatically motorized mechanism will keep shifting these contacts such that such an operation make your comfortable required voltage fed to the system. This way, a tap changing facility adapted to the transformer makes the system voltage controlled appropriately. By this has really substituted the loss of voltage. Means the drop in voltage due to inductiveness of the system, that is a reactive power only. We are trying to compensate the reactive power by taking care of whatever the drop has happened. That drop you are substituting or compensating by adding the taps or a voltage into the system to make it required as per your requirement. This is the facility being noticed. How this is mathematically viewed then? So just see a mechanism here. A transmission system where you can say this is basically a distribution system network where a mechanism is here. So sending end voltage at the primary of the transformer interface V1 and whose secondary is S. Vs nothing but sending end voltage. And here we have end of the transmission line with the R plus Jx impedance of the transmission line. End of the transmission we have receiving end voltage. So for this transmission line, sending end voltage, receiving end voltage. For this sending end voltage, we have a transformer with the tap facility. 1:TS ratio. This is called TS. TS is called off nominal ratio. So we have at the HV side tap changer facility. This is logically shown. You may ask me, just now we discussed this kind of a utility, why you are not shown like this, not shown like that. This is just to show you how the tap changer at the HV makes the required voltage at the secondary of the transformer or nothing but the transmission line sending end voltage using the taps. Similarly, I have receiving end side. This is called load side. Load voltage is V2. Load voltage is V2. Load side, I have a tap changer and I have a transformer interface with the TR:1 ratio. So turns ratios are such a way maintained 1:TS and TR:1 like that. This is the model of how in the distribution network transformers with the tap facilities are interfaced to get required terminal voltage V2 from the available voltage V1. So as a model, we have V1 getting transformed as a Vs and representing at the receiving end VR, VR getting changed as V2 for the requirement. Then this entire circuit is equivalent and represented at the load side. This has to be drawn as a conclusion of representation of entire circuit into secondary side or a load side. It looks like a simple. So it is the impedance and it is a primary voltage. When I transform it to the ends of this, that is a Vs. Vs become V1 Ts by Tr. We will see in the previous slide it is there. And when I reflect everything on other side, this impedance get transformed as R plus Jx divided by TR square, and secondary voltage remain V2, with respect to which all these voltages are transformed. Like you are transforming every impedance into a secondary side of a transformer. Induction motors representation equivalent at the stator side. How you do it? Like that, it is entirely represented into load side by a symbol representation. Let's come back to this, how this can be mathematically viewed. Let's say the tap changer, if V1, V2 are the nominal voltages, V1 at the input of the system, V2 at the load side, V1, V2 are the nominal voltages, then the voltage available at the secondary of the sending end side, what is that Vs? You can see Vs is V1 into transformers turns ratio Ts. So I'll come to this. What is Vs? Vs is, I'm speaking about this voltage. Voltage at the transmission section's entry point, sending end point is whatever the voltage I have here via the transformer 1:Ts. I am shifting it here. I can convert this. What is the voltage available here? Voltage available here is Vs. Vs is V1 into Ts. When I take a ratio of this, I can convert by transformers approach. I'll be getting Vs as V1 into Ts. Similarly, what is that VR? VR nothing but receiving end side, this voltage. What is this voltage? This voltage with respect to V2 received over here via the ratio TR is to 1. I can again write, what is VR? I can write how I wrote Vs equal to Ts into V1. I can similarly write, you can see here, VR, voltage at the receiving side of the section of the transmission is ratio TR terms into voltage received at the secondary side. So it is TR into V2 is VR, Ts into V1 is Vs. So I'll come back to this. So this Vs stand as V1 into Ts, VR stand as TR into V2. This we need to get from transformation ratios of this tap changers. So once I'm able to get from the given V1, V2, Vs and VR, we are able to get. Ultimately, what is our requirement? The requirement is what should be our required voltage at the load side. This is what I am trying to maintain. To maintain this, what is that ratio of turns I should keep here? What is that the ratio of turns I should keep here such that drop in the path, this is called impedance of the line, I into Z, is the drop total happening, that I have to compensate. Once I compensate, I'm quite sure from the available input voltage over here, by making use of these tap changers at the both the side, I can achieve required terminal voltage at the receiving side. That's called load side. This is my target. This is what certain PU, certain kV I want to maintain by the incorporation of tap changers in the system. Then respectively, what must be the sending end side tap ratio, what must be the receiving end side tap ratio, I have to calculate. To understand that, this is the mechanism shown you with the V1, V2 being nominal voltages at the sending end at the load side, and a transformer at the sending end possess Vs as Ts into V1, and transformer at the receiving side at its primary side, VR works as TR into V2. Now you can see the tap positions Ts and Tr are adjusted to compensate line drop. I was just speaking to you why I am using this tap changer. The voltage V2 I am unable to maintain as specified, which I am pumping it as V1 at the sending end. The drop is tremendous and which I need to compensate. To compensate that, the tap settings at the primary side and the secondary sides of the transmission section I am altering. So Ts and Tr product made equal to 1 for the design of the particular transformer mechanism or a transmission system incorporating tap changer at its ends has a design criteria, the ratio or product TS into TR. When I take a product, it is made as 1 for the design consideration, so that we have minimum range of taps on both the transformers and the order of the voltage level remains the same, because ultimately V1 is equal to V2 if I want to maintain. Then what is that a drop happening in the system transmission section? I have to compensate by shifting the certain tap ratio at the sending end and certain tap position at the receiving end. Together these will help to retain required V2 from the sending end voltage V1. That's what is the nominal voltage is maintained here. Let us now transfer all the quantities to the load side, which I was speaking to you. The line impedance being R plus Jx, which is to be transferred to the load side as R plus Jx divided by TR square. You must be knowing shifting of impedance of a transformer from primary circuit to secondary and secondary circuit to primary. You might have learned in T and Z, or most probably you remember this. Shifting that impedance, when I do it, it becomes TR square, ratios square. And the voltage, when I take input voltage to the load side voltage to represent V1 in secondary side, it is V1 actual, TS by TR as the ratio. For the impedance become TR square. For the voltage it become V1 into TS divided by TR. So it may be, you may need to recall it, or you will be remembering it, how the impedance of the primary circuit get transferred to secondary divided by transformation ratio square you are doing. When you are transforming voltage from primary side to the secondary side of a representation, the value of voltage divided by the ratio constant you are doing. So this equivalent circuit, using this, we can draw the equivalent circuit as shown here. You can see here the representation of this V1 into the secondary side, it become V1 TS, which is the input, divided by TR, shifting it to the secondary side. Then this impedance which is connected here, I shifting it to the secondary side, taking this care as R plus Jx divided by TR square. And secondary side voltage is as usual V2 itself. So with this, what I can do, sending end side profile, receiving end side profile, I take care. The arithmetic drop, voltage drop is obtained from that diagram as delta V. Because this is the drop, I have to compensate by changing the TS and TR such that this drop is addressed by the transformer and certain expected voltage V2 is maintained. In that due respect, you can see the sending end voltage for the model is V1 TS by TR minus V2, which is nothing but this one. V1 TS divided by TR minus this V2. Now that become a differential voltage between sending and receiving end side, which is written here, delta V, which is equal to, you just recall back when we are studying the sensitivity of the voltage and powers, when we were defining, we got this equation Rp plus Xq by V2. So now TR square into V2. So we got to know now, in case of tap changer facility provided transformer, between the sending end of the section and receiving end of the section, when we measure the delta V become V1 TS by TR minus V2. It is closely equal to Rp plus Xq by TR square into V2. And we have just taken here for a design consideration, TR into TS product is considered as a 1. Using this TR into TS equal to 1 in this equation, we can simplify delta V as TS square V1 V2 minus V2 square equal to Rp plus Xq. This term, when I take other side, simplifies it. This term RHS denominator, when I spread other side, it become the TS square V1 V2 minus V2 square equal to Rp plus Xq into TS square. So by this, what exactly I am going to achieve? My ultimate achievement in this discussion is, how is that delta V is addressed? What is that TS and TR I have to set at the input side and output side of a transmission section such that the end voltage at the load side is at my control V2. So for that, my next step is to see to it that This deviation, delta V, or a drop in voltage is compensated by taking TS and TR suitably at both the sides. You can see here. So therefore, when I work this, when I simplify this equation, rearrange it, it becomes a quadratic form, second order equation, V2 square minus TS square V1 V2 plus RP plus XQ inside bracket and TS square equal to 0. So this will have two solutions. When I solve this for a certain required V2 is my requirement ultimately. This is called as for a required receiving end voltage. What must be the sending end voltage? I'll be knowing V1 also. And only the value of TS, if I work here, I'll be able to get what is that cap position, which will surely maintain V2 from the given V1 profile. So this way, I have to use the possible best solution out of that. By this, what exactly we have done? We have taken care of drop in the transmission section. That drop is due to the reactive power absorption. Then what is that reactive power you have really pumped in by having tapped or taps changed according to your requirement? That is QT. That is QT is equal to T outside. For a capital T in or TST, invariably T has taken T outside 1 minus T inside the bracket V square by X, nothing but T in outside the bracket 1 minus T into short circuit complex power, SC. So this is what really we have substituted or compensated in terms of reactive power to retain our required secondary voltage or required V2. V2 was the ultimate requirement to maintain certain PU V2 from the input side voltage V1. How is that TR helped me? Why? By having modified the TS and TP by design, changed them to a suitable tap number, you have compensated the delta V. That delta V's drop is root cause by what? Reactive power. Then what is that reactive power? Indirectly you have injected or compensated. That is QT. Total in the system is T inside a bracket, T outside a bracket, 1 minus T complete and SC. You can see here, if T is less than 1, QT is positive, then the VAR flow is from sending end to the receiving end. This is an observation from the system. When you have interconnected operation of this transmission line, reactive power float from forward sending end to receiving end to sending end, depending upon the system's ratio here. You can see when T is less than 1, QT is positive. Definitely it is a flow from sending end to receiving end. If T is larger than 1, you can definitely see this equation changes its dimension or its direction also. So QT is negative at that time. That is the flow out of VR. It comes towards the sending end side. This way, by having suitable TS and TR chosen at respective ends of the transmission section, the reactive power flow can be moderated or controlled by having adopted delta V compensation by tap changings. This is how this simple theoretical concept of tap changing with the numerical change what we'll get can be understood. So similarly, I have booster transformer. The another application is booster transformer. Booster transformer, as we know, the meaning boosting means elevating it into a higher. So for this to understand, I have 3 diagrams. You can see there in the top line A, B, C. 3 figures I have shown from different books and another book I have taken. So the first one is single phase. First of all, these are all single phase representation per phase. So I have a line. You can see the top line. You can just watch my mouse cursor, line and a return line. Then the line and return line have one regulating transformer that we have to understand. The requirement of booster transformer is they have between a line and a neutral, they have a regulating transformer. Secondary of that is tapped. Like a selector switch provision is provided here. You can get any differential voltage from any 2 points. That's called a tapped. Then there is another transformer which is called as a booster transformer. Now you see its a secondary is in series with the line. You can see this is a line continuous. This is a transmission section continuously flowing or moving. This is a return line for a single phase representation. The secondary of the booster transformer is in series with the line, and whose primary is connected to the secondary of the regulating transformer. What is that? Primary is the one to which we inject the power. Secondary is the one on whose interconnection with the primary secondary, the voltage which is induced in the secondary of the booster transformer get added to the line voltage. Let's say there is a V volt here. This may be delta V I am injecting. V plus delta V become available voltage over here. I am boosting it by delta V. If the polarity of the voltage which I am connecting to the primary of the booster transformer, if it makes V plus V, it is to boost it. If this is opposite to that, it will opposite. It will reduce the voltage. V minus delta V like that. That is by provision over. You can see this regulating transformer is having a tapped secondary. Secondary leads are such a way connected by a selector, reverser. The value, the lead 1, the lead 2, you can watch here. One of the lead is either the beginning of the winding or closing of the winding. Can you see here? This contact may be connected permanently to 1 or it may be connected to 2. Hope so, one of the contact is maintained. The other end of the winding is floating selector. Any one of the tap which is connected, depending upon the polarity or its additive or subtractive nature, the induced voltage in the booster's secondary makes its impact to the line voltage here. The voltage was V here. If it was additive to the line, it become V plus delta V. If these two lines are crossed, reversed, automatically the voltage available at the outlet of this is V minus delta V. So this delta V is controlled by your taps. Tap may be 0.1, 0.2, 0.3. Depending upon the value of the voltage you are trying to inject to the booster's secondary, makes the available voltage at the line either plus V or plus delta V or minus delta V. This we call as booster transformer. This is used in medium and long transmission lines. The same concept is mentioned in this main transformer. You can see here there is a distinction between these two. There is a continuous transmission line. Across the line we have a regulating transformer. This is what is shown here. The different diagram from the different book is main transformer is having a primary input. Secondary of that, can you see here? Secondary of that is continuous line. There is a tertiary winding. You can see inner, there is a third winding. Primary, secondary, tertiary winding. Tertiary winding, I was speaking in the earlier discussion. Tertiary winding is usually used for compensating devices. The compensating devices, phase modifier, all such devices are connected to tertiary winding of a transformer for their action. So tertiary winding is having the same mechanism. This entire assembly you can visualize as a tertiary winding of a transformer, whose again reversal, forward, taps are connected to booster's primary. Booster's secondary is in series with the line. Again, whatever is the voltage available here is V plus delta V depending upon the polarity, or V minus delta V depending on the polarity can be seen. This is another way of booster transformer. The third view, this is from Kotari textbook, I remember it. So this is a transmission line. Only one line is shown, the incoming line, correct? This line is shown by a line, and return line is shown as a ground here, correct? Between line and ground, there is a transformer's primary connected. It means this is charged to a certain voltage. This primary winding, this is secondary of that. So secondary is in series like this. Primary winding, secondary winding of a booster. Secondary winding of the booster is in series with the line. It is true here. This line is going continuous. Let's imagine simply continuous. Yes. Secondary of the booster transformer is in series with the line, and primary of that is connected to line and ground, return line. Then you have two special contacts. What is that? Relay 1, relay 2. Relay number 2 contact is making it connected physically. When the contact R2 relay is closed, secondary is in series. Can you see this? When this contact is open, can you see induced voltage in the secondary won't get added to the line voltage to get a revised voltage here. That's called when R2 is on, secondary is in series. When R2 is open, secondary is not in series. Instead, R1 will be on at that time. So R1, R2 are complement to each other. When R2 is on, engaged, R1 is open. When R1 is engaged, R2 is open. You can see what will happen if R2 is open. If R2 is open, secondary value of this will not get added to this. The line continues via this bypass. You can see via R1 relay contact, it continues. So therefore, this is another way of representation. You are directly adding delta V, whatever is the voltage it can add, certain magnitude delta V, because there is no tap changer like this. Simply a voltage induced in the secondary getting added to the line. When R2 is closed, get added to that. If R2 is off, open, you have only one path, line can continue as usual via the R1 to the next one. So this is called booster. So these two contacts are logically controlled depending upon your requirement. So this is called as booster transformer concept by conventional transformer. The same thing can be buck boost like converter, how we say in power electronic converters. The similar phenomena we can see boost or buck or reduce it by changing the polarities of this can be done by transformer approach. The another way of controlling the voltage is voltage control using phase shifting transformers. You can just see a diagram basically. I have been given a diagram with the RYB three phase and line R. First line is having a booster transformer like approach. Secondary of the booster transformer is in series with the line R. Primary of that is connected to a transformer which is connected between rest two lines. When I am compensating an R line, Y and B are my other two lines. Across that there is a transformer. You can see there a transformer with the voltage VYB primary induce an EMF V dash YB in the secondary, which is connected to the booster's primary. You can just see this diagram is so easy to go. This booster's primary is having a supply from secondary of a transformer which is connected between two lines Y and B. So this is shifting the voltage in the line. How is that? Just you can see. You can just see a vectorial representation. VR voltage in line R, correct? VY voltage of line Y. VB voltage of line B. I am speaking about these line voltages. So what is that compensation shifting in phase you are doing, that we need to understand. For that, we know that whenever power transfer takes place from bus 1 to bus 2 through a transmission section, we know that active power transfer is given by P12, V1, V2, the terminal voltages of the bus, X12, the net reactance of the path, sine of the angle difference between bus 1 voltage and bus 2 voltage, like delta 1 minus delta 2. This is the active power transfer. Similarly, what is that reactive power transfer among those two buses? How is that dependent? Is given by another equation Q12. Q12 is given by V1, V2 by X12 as usual, and this sign changes cosine. Cosine delta 1 minus delta 2 minus ratio of V2 by V1. This becomes Q12, reactive power transfer from bus 1 to bus 2. This is what theoretically we must be knowing. Now let us come to compensation, shifting in phase where it is being done. So the shift of this VR is taken. VR, Vy, Vb. So VR will not be VR. VR is getting its shiftment by this way we can see. So what is VYB? If you know star and delta kind of phase and line relationships. VYB, line to line voltage. We know that. It is the line voltage between Y and B. So VYB. VYB is what? VB minus Vy minus Vb, like a phasor differences. Similarly, you are taking VYB line voltage. You are taking its secondary value VYB dash in the transformer that is connected to the booster transformer's primary and injecting into the R phase. Nothing but you are trying to modify the phase of this R. What is that phase? Phase is an angular displacement that the vector representing got shifted from the reference. That's the phase. So phase of R vector is getting modified. How is that? Originally phase VR is at this mark, 120 degree Vy, 120 degree Vb, a three-phase vector. How we can write? Now you will find this VR, whatever I am having, vectorially compensated by a induced voltage here, which is V dash Yb. You can see VR is having vectorial subtraction. There is a shift here. So downward arrow shows you V dash Yb. This is an induced voltage in the secondary of the transformer which is used, getting vectorial addition with the VR. That is making the resultant VR as VR dash. We are modifying the phase of R, which is VR at certain position. That position by an angle alpha got shifted. That shift is brought by injecting voltage into this line by the voltage of Y and B remaining line. So this vector which is shown downward result VR as VR dash. When VR is shifted as a VR dash, what is the angular shift you got? This is called an alpha. This is called phase shifting of a certain phase. This is one single phase representation. Single phase representation require two transformers. One is between two lines and the one which is compensating the actual line. R line getting compensated, we require a transformer between Y and B and a injecting booster at the R phase. So this way you will find vectorially there is a shift of VR down to VR dash. By this way you have injected reactive power into the system. That reactive power flowing on the system being given by Q12, like this way. So this is a theoretical concept. Just try to visualize the hybrid notation here. If it was a single phase concept like this earlier which I showed here, this is a booster only. In the same group, R line, return line. In the R line only you are trying to add it. No vectorial difference here. The difference between this diagram is, no doubt delta V we are doing. Either you are adding or subtracting. Depending upon that, there is a resultant VR. How is that VR? Taken from other two lines. This is making a shift in vectorial position of that. This is meaning called as phase shifting. So this is done by a transformer's approach only. Hence, this way we can control the voltage by shifting the phase. So ultimately phase become a power factor angle in composite relation of that. So therefore, we can just see not only a tap changer, not only a booster, even a phase shifting transformer also help to control the voltage of the system by making use of the phenomena shiftment of phase of a certain vector. Then, how exactly these help or how these are really important to us? The voltage stability and instability is another important aspect of power system operation. Ultimately, power system operation control is with the objective operation of the system in a very stable mode by suitable generation, delivery and managing the contingent changes even after experiencing differences or disasters. So for that, voltage being one of the important aspect, voltage stability is to retain the nominal voltage within the permissible range by adopting suitable compensating mechanisms, suitable methods such that voltage will not violate its specified bands beyond. Therefore, it is to feed, it is to provide basically reactive power, because there is a vital link, strong interdependency of voltage and reactive power, frequency and active power. When I take into account voltage, when I speak, when do system is not able to maintain its stability, is unstable, when it delivers its service to the loads, due to the reactiveness of that, due to the demand reactive power, voltage get affected. Stability with respect to not being maintaining its voltage within the range specified become a threat and challenge. So instability is resulted. This is very oscillating phenomena, and it will protrude into the system and cause many of the components to start oscillating and fail and malfunction. Therefore, voltage stability is a very important aspect of the system's security, healthiness, securedness, whatever you speak about, it should be there as an inherent capability. Therefore, that is challenged whenever system is suffering deficit of reactive power. Therefore, we must be careful about voltage stability or instability aspects are questioned or challenged whenever system suffer deficit of reactive power. Now, to quantify that, we have some mathematical equation. If I know the current I square in complex notation, I into I conjugate. So I can rewrite this I square as P plus JQ by V into P minus JQ by V conjugate. By this way, if I multiply and get the resultant, square of the current in the complex mode results on the power what the system is handling, P square plus Q square over terminal voltage square, V square. When I take that quantity represents I square. So why we are trying to do this? Because the loss due to active power component I square R, nothing but your resistive part of which, and loss due to reactive power component inductiveness is always measured with I square R and I square X. To compute it, we require the current in terms of the system's active power, reactive power and working voltage levels. In that notation, it is a representation by current square equal to P square plus Q square over V square. This becomes very necessary for us to understand. For a certain terminal voltage to be maintained, for a certain reactive power to be delivered, what must be the power factor of the system? If you want to calculate, these are all the equations I'll be utilizing. Therefore, I square is P square plus Q square by V square, and real power loss I square R can be written by this equation, and reactive power loss can be written by this. Because a certain load is drawing a reactive power at the end of the transmission section. Throughout the transmission length of L kilometer, system reactance dominates. There is a drop I square X in the line and reactive power absorption at the end of the line. So reactive power has to be fed to the load, as well reactive power drop happening in the line has to be met by the source again. Source find two parts. One is reactive power demand of the load and reactive power requirement of a transmission section. To compute that, these equations help me. So therefore, this complex I square will help me to get I square R and I square X. Most of the numerical problems are inductively dominated. Preferably, I'll be using I square X only, not the I square R. Okay. Then, what are the causes of instability? So a power system is with a small disturbance may be stable at a given operating point. If followed by a small another disturbance, voltage near the loads are identical or close to pre-disturbance values before the fault. A fault or a power system at a given operating system subjected to a given disturbance undergoes voltage collapse. Another keyword, let me get to this point. Voltage collapse. The keyword collapse mean massive fall of voltage. Collapse of voltage means decrease of voltage rapidly as the load increases on the system. This is called active power demand continuously increased or step load on the system cause voltage to fall seriously. That we call as a collapse. If post disturbance equilibrium voltages are below acceptable limits, it means the voltage collapse, voltage or any disturbance which after having recovered from that levels are very below, mostly system is not able to stable. So voltage instability is the absence of voltage stability. That's the keyword, exactly contrast to each other. When the system is not able to retain its terminal voltage at the specified buses to the specified range, definitely it is an inability, we can mean it. Inability or lack of that reactive power strength in that, lack of or a deficit of reactive power which it would have substituted or subjected to the requirement, is not able to do, then it suffer drop of voltage or collapse of voltage. So this is how system's inherent inability is absence of stability stability with respect to voltage. That is due to absence or lack of reactive power in abundant. That may be the reason instability is resulted. To overcome this, a study must be performed. Stability aspect must be worked out, and stability analysis reveal what is the need, when all, and how much, and where all it need to be. So this study has to be performed as stability analysis. On that stability, we have so many parameters, short term, medium, long term, depending upon the system's operational scope, they must be worked out. Basically for us, system's inherent inability or lack of control, lack of the reactive power subsequently, or anything which is making it feel not able, unable, that is the reason for instability we can mean from this. So therefore, the other voltage instability classified into, or you can say voltage instability can be classified into transient stability or long term. I was speaking about short term, medium term, or long term, depending upon the duration, how long such an inability is visualized, that is classified as transient and long term. Transient stability means what is a very massive, in fact, fractionally occurring and disappearing. That's a transient. It will appear and disappear very fractionally. Long term, it is a stable, sustained failure, fault, inability over a duration of time. That is classified. Transient voltage stability has a time frame of 0 to 10 seconds. Within that 0 to 10 seconds, any massive fault, failure, disaster occur and disappear. So this time frame must be very sensitive. During the short circuit, you can see this may be due to short circuit. When the voltage dip is severe, suddenly a heavy transmission, HV transmission section get short circuit, massive collapse of voltage occur there. From that, definitely reactive power to pump into system doesn't work, may not be able to do it. So this is one of the reason it may be a transient stability threat within the 0 to 10 seconds. Or voltage collapse can cause during islanding. So when we see a power system states of operation, steady state, normal, alert, emergency, extreme emergency, restorative, during that islanded mode of operation, extreme emergency situation, entire power system is cut into small pieces of work. Some generator at one side alone, some loads with some generator or only loads. So during such collapses, there is a drop of voltage due to sudden loads with a very small generator ability, or there is a sudden fault, generators are not able to cope up the terminal voltage, that may be an islanded operation, we may find it. If the imbalance in the island is more than 50% of that capacity, voltage decays faster than frequency. You just see it's a very serious phenomena. Voltage collapse. When I go to the next portion, we have a plot of PV and QV curves. Plot of voltage and active power curves. How is that? Massive loading effect. Higher power, active power demand from the system cause voltage to fall seriously. At certain point of loading rate, voltage will not be able to retain its voltage. It will fall very drastically to zero. So that PV curve, QV, reactive power with the voltage relationship, plotted as a QV curves. Those PV and QV curves help us to understand system's ability to cope up or experience such any disasters possibly will be studied. So there is one we can say, so voltage decays faster than the frequency. Thus, under frequency relay may fail and may fail to operate to permit load shedding. These are the consequences when one of the component interconnected in the control section start malfunctioning. The next cascaded or other devices depending upon that start malfunctioning, and some expected functionality, even though it is healthy, they may not function. So this is how adverse effects of that in a micro or short time frame run like this. Integration of HVDC links into weak power system may cause transient voltage stability problem. Just see, it is an integration of high voltage DC links to weak power system. The weak power system can be characterized as a old one, not yet modernized, past many years, the same old transmission line, same conductors, not yet modernized, same transformer, switching components were almost to be modernized, not responding timely in frame. Latest state of art switch gates are not used, and it is sluggish, highly inductive system, poor performing, that we can classify as a weak power system. So that weak power system having an interface with the HVDC link, a high voltage DC link from that get extended, or from HVDC it is getting respond input to which. So there must be a transient voltage stability problems. So system is already a weak, it's a reflection on any such subsequent changes won't come in time frame. Definitely system will suffer from this. That would be one reason. And long-term voltage stability problems typically extend over 2 to 3 minutes. See that again, time within 2 to 3 minutes of time frame, maybe a sustained faults or stability problems are challenged. Then during which some of the actions, loss of generation, transmission line, cause high reactive power loss, or voltage sag, or even OLTCs change caps to restore loads, etc. would be the cause. Therefore, any of these cause definitely challenge the voltage instability. And rapid load growth, this is the fifth point I'm trying to say. The load growth is rapid, megawatt per minute. This is a rate of rise of load. This is another important aspect of power systems' ability to cope up with such loads which are building rapidly. If that is not able to generate adequate megawatt for the timely need, definitely systems suffer. That will cause a voltage not to be stable. That's why we know megawatt transfer between two buses P12 is what? V1 into V2 over X12 sine delta 1 minus delta 2. There are terminal voltages. So because of active power transfer, higher demand you are causing megawatt per minute change, rapid change. Definitely, while transferring it, generators need to cope up. When they cope up, they need to boost their terminal voltage and V1, V2, and there occur a fall. V falls, definitely P12 falls. This way, there is a link between active power and voltage as well. Even though there is a rise of active power, there is an impact of that on voltage as well. It is not only the reactive power cause a change on voltage, it is indirectly active power also causing link or causing a changes on voltage. Thus, voltage stability is an important aspect. It is predominatingly concerned with the load areas and characteristics. Hence, it is basically a problem of load stability while the rotor angle stability is a program or a problem of generator stability. So it has to be classified and studied carefully. Then only the proper operation is possible. Then parameter which indicate voltage strength. There are about 5 parameters. So the one is voltage strength of a system can be gauged from the following certain parameter, like which we were understanding. Control of voltage and reactive power is our heading. So how do you gauge, how do you ensure the strength of the voltage is good or not, or what is that ability with which by a measure? That measure is by short circuit capacity, the first parameter. The short circuit capacity is the short circuit MVA, apparent power given by SC. Short circuit complex SSC is MVA equal to √3 VL, line voltage into short circuit current, where ISC refer in kiloampere and VLL refer in kilovolt. Together in per unit, it refers VPU, IPU equal to 1 by XPU. So it is nothing but short circuit capacity of a system is 1 by reactance of the system itself. That is, XPU is the system Thevenin's impedance. So the assumption here is that voltage is close to 1 pu. Voltage is close to 1 pu. The short circuit capacity is the measure of voltage strength. So this is how the strength of the voltage of the particular system is measured using short circuit capacity by taking this consideration. Short circuit capacity is the measure of voltage strength. I am in need of voltage strength, that itself is 1 by X of the system. So a high capacity means the network is stiff, or in other words, the changes in load will not significantly change the load magnitude or load voltage magnitude. Therefore, this is one performance measure. Strength of the voltage is measured by short circuit capacity, which is 1 by X. So you can say higher the X, lesser the strength, you can say. You can just remember it. S is 1 by X if I say. System is highly inductive, poor, ill conditioned. So 1 by X, large value of X remains, S equal to very small. It means that definitely makes the strength of the voltage in a very ill conditioned system is very, very low and poorer. That way, system must be good enough. Optimum value of X must be there, because system is inductive, no doubt, but highly inductive system is not desirable, because that affect your voltage strength, that challenge your voltage instability. In that due regard, you need to see system must be stable enough to maintain proper voltage strength. The another parameter is short circuit ratio of generator. It is coming to generator side now. Earlier we were on system side, transmission side. Now it is on generator aspect. We call it as SCR, short circuit ratio. Short circuit ratio of a generator defined as 1 by transient reactance of the generator, 1 by XD. Then it is equal to ratio of field current to produce rated voltage on open circuit to the field current to produce rated current on short circuit. Nothing but voltage to current ratio. Field current, what is that field current at the synchronous generator side you are trying to inject to get a certain open circuit voltage defined to the ratio of current injected in the field circuit to produce rated current on short circuit. Now how you do open circuit test, short circuit test, how you perform, you will be aware of that. What is the open circuit voltage, what is the short circuit current, like that. Those two parameters of a synchronous machine, if I take a ratio open circuit voltage to the short circuit current of that in the field notations, field current notations for those requirement, if I take a ratio, that become 1 by XD. XD stand as synchronous machines direct access reactance. So what exactly it's tell you? It tell you that synchronous machine is the basic source of reactive power. We all are aware, and that was our beginning of reactive power generation ability. What is that capacity each synchronous machine possesses? It is this. SCR is the configuration. SCR is the individual ability of the synchronous machine to support reactive power requirement. That is defined by short circuit ratio of the machine. So therefore, we should be careful. SCR is 1 by XD. That definitely tell you what is the ability of the machine to support your reactive power. In turn, that will shift your voltage strength. Therefore, point 2 is SCR. 1 by XT defines it from the generator perspective. That's what I was speaking. Can machine, synchronous machine, deliver whatever the infinite reactive power like active power? You cannot do. That's the limitation. What is XT? Winding configuration. This is the terminal. XD notation is from winding perspective of the synchronous machine. I cannot change it however I want. Once I design a machine, configured and ready to fit, XD is defined. I cannot modify it however I like. Therefore, that is an inherent ability with the synchronous machine to supplement required reactive power, which it can support to retain a voltage strength, that is 1 by XD itself. I cannot increase this beyond. That is the reason, even after this, if reactive power requirement is increasing in the system, I have to compensate artificially by condenser, synchronous condenser, fact devices, capacitor, inductor, etc. They have come into picture. When synchronous machine cannot do, they are the alternatives doing it for me. That's the meaning. The minimum and that is the maximum ability is SCR itself. Therefore, having this viewed, so this definitely makes one sense of point. The next 3 parameters are like this. Short circuit ratio of equipment. When it comes to an equipment operating on the system, it's the ratio of short circuit current capacity to the rating of device. For example, you can see 1000 MVAR compensation has a short circuit ratio of 5. It is speaking about a compensating fact device, you can imagine, whose SCR, short circuit ratio, is 5 in the system, which means 5000 MVA, whose SC is 5000 MVA. A high SCR means good performance. SCR must be good so that it can definitely make the system stable. This is from compensating perspective. Like I have a capacitor, inductor through a SCR, switching component, or a MOSFET, IGBT. I devise a component to compensate. That is possessing a very good strength. Definitely that is making systems reactive power requirement fulfilled. Then voltage strength is superior. So voltage strength depends on short circuit ratio of the equipment used for compensation. Then effective short circuit ratio is another parameter, ESCR. It takes into account of shunt reactive equipment also at the location of the equipment. This is with respect to previous point. Previous point is an equipment which is there to support your requirement. Along with that, any shunt components which are there, whose equivalent response, collective response is taken. So the account of shunt reactive equipment also at the location of the installation of the equipment. A synchronous condenser increase the fault current and hence short circuit current capacity also. Likewise, you can connect to this. The last one is voltage regulation. The voltage regulation can be obtained with the help of the following equation. Delta V is a small infinitesimally change in reactive power to the SC. Then it can be written as V equal to the internal voltage E inside a bracket 1 minus Q by AC. So these 5 parameters